Today's episode was definitely a harder one to research just because I'm doing large-scale structure formation today, and that talks about the formation of the galaxies and the early suns, or stars, and I wanted to do this in a linear kind of structure, like a storybook timeline, and for this episode I'm not going to be able to do that, mainly because there's an infinite number of these, and I'm not going to go into when each one was formed. So what I'm going to do is talk about it in kind of like a hierarchy, with the smallest structures forming before the larger ones. And so today I'll be going through the early structures from oldest to newest, and to do that I'll have to go from smallest to largest. And the first structures to form are quasars, which are thought to be bright early active galaxies, and population 3 stars, which are extremely metal poor stars. So that's going to be kind of the gist of today. We'll get into like the formation of the Milky Way galaxy and just a lot of cool things like that. So hope you guys enjoy. Alright, welcome back to Down the Line. I'm your host, Pete, and we're going to start with reionization. That's a process that caused the matter in the universe to reionize after the lapse of the Dark Ages. Reionization is the second of two major phase transitions of gas in the universe. The first phase change of hydrogen in the universe was recombination, which occurred at 179,000 years. That I think is from 2 episodes ago. We talked about that, so if you go back you can hear a lot more detail about that. But basically what it was the universe cooled down to a point where the rate of recombination of electrons and protons to form neutral hydrogen was higher than the reionization rate. So the second phase change occurred around 1 billion years after the Big Bang, once objects started to condense in the early universe that were energetic enough to reionize neutral hydrogen. Giant clouds of these primordial elements collapsed to form the first stars, whose ultraviolet rays heated the surrounding medium, once again stripping the hydrogen of its electrons. This is the last major change in the early cosmos makeup, as the universe remains ionized today. So at about 400 million years, the universe was 50% ionized. Dwarf galaxies contributed nearly 30% of the ultraviolet light during the process of reionization, because 50% of the ionizing photons are able to escape dwarf galaxies as opposed to larger galaxies. And I'm actually going to get into dwarf galaxies in a little bit. I'll get kind of in depth with all of these different galaxies and these different events that happened that contributed to reionization. At this point, the smallest galaxies dominate. However, they basically kill themselves off by blowing out their gas to their own supernova and heating their environment. I'll also get into supernovas. So, afterwards, larger galaxies, but still much smaller than the Milky Way, take over the job of reionizing the universe. These galaxies are called dwarf galaxies. And dwarf galaxies are galaxies 1,000 times smaller in mass and 30 times smaller in size than our own Milky Way. They formed in the first billion years. The universe became fully ionized at around 860 million years after the Big Bang. It's still uncertain as to what objects provided the photons that reionize the intergalactic medium, which is the hot X-ray emitting gas that permeates the space between galaxies. To ionize neutral hydrogen, an energy larger than 13.6 electron volts is required, which corresponds to photons with a wavelength of 91.2 nanometers or shorter. This is in the ultraviolet part of the electromagnetic spectrum. So basically, to ionize neutral hydrogen, it had to be in the ultraviolet part of the spectrum. So now to get into the first objects that were formed around the time that the universe was trying to reionize itself. And the smallest and oldest one that we have are called quasars. They're also called Quasi-Stellar objects. And what these are active galactic nucleuses of very high luminosity. And the definition of luminosity is the total amount of energy emitted by a star, galaxy, or other astronomical object per unit of time. My definition is it just measures the brightness of it. So these things are just in the center, they're like the nucleuses of galaxies that are just super bright. They inhabit the very center of active young galaxies and are the most luminous, powerful, and energetic objects known in the universe. They began forming at about 400 million years after the Big Bang. Next, we'll get into population 3 stars. And what these are extremely metal-poor stars. They were most likely the first stars, but they're hypothetical and inferred from physical cosmology. They've yet to actually been observed directly. These stars have no elements more massive than hydrogen or helium. They are a possible mechanism for reionization when a supernova explosion occurs. Supernovas are what occur during the last stellar evolutionary stages of a massive star's life. The massive explosion creates a new bright star before slowly fading from sight over several weeks or months. The supernova explosion produces such heavy elements so hot and large that population 3 stars could have contributed to reionization. Even without direct observations of population 3 stars, they are actually still a compelling source. And so, a brief summary of that, I guess, is that these population 3 stars are just hydrogen and helium, and at the end of their life, they have this massive explosion, which are called supernovas, that are so just crazy that once the explosion is left over, there's a new star that just burns really bright, and from the explosion, you get these new elements, these heavier elements, metals, that are created from it. And these actually go into what made newer stars today. Now here's a side note that I had. It didn't really fit into the narrative that well. This is like the best place I could get it, but I just thought it was too interesting not to put in. In June 2015, astronomers reported evidence for population 3 stars in the cosmos redshift 7 galaxy. Such stars are likely to have existed in the very early universe and may have started the production of chemical elements heavier than hydrogen that are needed for the formation of planets and life as we know it. I'm going to add this the source to this article in the description with the other sources. I just thought it was super interesting that we might actually have a little bit more evidence to prove these stars to be true. Next, I'm actually going to get into galaxy formation and evolution. And this is going to go into kind of like how the Milky Way was formed. I'm not going to talk specifically about the Milky Way being formed, but the formation of galaxies like the Milky Way, like in any kind of galaxy that kind of falls into that line. So this is basically how the Milky Way and just an infinite number of other ones have been formed too. So galaxies actually started forming when large volumes of matter collapsed. Population 2 stars, which are metal-poor stars, are formed early on in this process, with population 1 stars, which are metal-rich stars, forming later. And so our Milky Way galaxy is actually called a spiral galaxy, and it's the earliest state in the evolution of galaxies. When formed, it has a disk shape and is called a spiral galaxy due to its spiral-like arm structures located on the disk. These structures could have formed in one of two sequences, the top-down or bottoms-up theory, and I originally had like super long, like it probably would take me 10 minutes each to talk about these. That's just way too much, so I'm going to give a simple explanation of both of them. So either large structures the size of galaxy clusters form first, then later fragmented into galaxies, which is the top-down theory, or dwarf galaxies formed first, then merged to produce larger galaxies and galaxy clusters. So galaxy, groups, clusters, superclusters, I'm going to talk about all those probably at the end of the episode. They're just, I mean, that's getting to a point where the universe just is at this point, and we're starting to kind of give them names and grouping them into certain things. So I thought I would add that at the end, just kind of what people have done with the galaxies and like how we've kind of structured them ourselves. One thing is that I thought was interesting too is that galaxy mergers can occur when two or more galaxies collide. They're the most violent types of galaxy interactions, and it's a fundamental measure of galaxy evolution. The Hubble Ultra Deep Field, viewed from the Hubble telescope, shows a number of small galaxies merging to form larger ones. And that's actually how the Milky Way kind of became bigger, too, was that you have these small galaxies that are just, combining, not even combining, they're just crashing into each other. And what's left is a bigger galaxy. So that happened to the Milky Way before, and we're actually on like a collision course with the Andromeda Galaxy right now, which is pretty scary. I mean, it's not gonna hit us anytime in anyone's lifetime right now, in 2017. I mean, if you're listening to this like 1,000 years from now, get worried because it's coming. I have actually no idea when it's even supposed to hit. The Milky Way is actually estimated to have begun forming about 13.4 billion years ago. And that's another thing I want to talk about here is a lot of these dates and years and everything like that at this point in the universe are just, I found like 5 different sources all saying different things. I went for the one that said the most, like if this one says 13.4 billion years ago, I said this one, I chose this source because I found it the most. Compared to like other ones saying that it formed, sooner or later. I just went with whatever I thought was like the best source. So now I'm going to get into the types of galaxies, like groups, clusters, like all that stuff that I said I'd save for the end. So there's these galaxies, and when you get a certain amount that are together, we call them groups. And so clusters are hundreds of galaxies bound together by gravity. So you have a bunch of groups, and these become clusters. And superclusters are large structures of smaller galaxy clusters or groups, and they're the largest known structures of the cosmos. So basically you just have people see, a group of galaxies, and then they see multiple groups of galaxies. Well, those are a cluster. And then you see multiple clusters. Those are superclusters. It's just people, trying to zoom out of the universe. That's more of a man-made idea than I think what it actually is, which are just a bunch of stars and galaxies just happen to be right next to each other. But yeah, that's about the end of large-scale structural formation. What I'm going to get into next, the next, I think, logical leap would be to go to the evolution of the solar system, starting from the beginning of when it formed to in the far future when it will have ended. So that's going to be a really fun episode. I already did all the research for that one, so I'll see you guys next time when we do that. And thanks so much for listening to this one. Let me know if you guys liked it, and I just hope that the information wasn't too convoluted for this one. There's a lot of information, and I tried as best I could to kind of make it in a linear structure, but I know that there's no way I could have done that in a good way, so I feel like this was the best way, talking about the smallest objects and just going out until you hit the superclusters, which are just the biggest things in the universe that we have any idea of. So thanks so much for listening, guys, and I'll see you next time with the evolution of the solar system.